welcome to this webinar. So this is an overview of JAX. I'm not going to go into nitty-gritty details because we only have 1 hour. It's the very first time I'm presenting this topic. But I really like JAX, and there will be more webinars to come. So this is just to give you a taste of what JAX is and hopefully convince you to start learning it. But there will be more advanced webinars following this. A little bit of context. First of all, what is JAX? It's not an insanely popular language for some reason, which actually leaves me fairly surprised. So for those of you who have never heard of it, never looked at it, what is this? So it's a library for Python. So you can access it using Python code, but as we'll see, Python code that has to be a little bit special. It's a tool developed by Google. The central data structure is the multi-dimensional array. So very similar to the ND array of a NumPy that I'm sure lots of you are familiar with, or the tensors that TensorFlow or PyTorch use. The main thing that JAX is great at is to take numerical programs that use those multidimensional arrays and do transformations of them. So one of the transformation is automatic differentiation, but there are others. And all of those transformations can be composed in any number of ways, giving it a powerful way to transform programs. And this is particularly useful in the context of machine learning for deep neural networks. Also, it has the ability to compile programs for any hardware, so CPU, GPU, and TPU, but was mostly built with accelerators in mind. So it's really oriented to be used with GPU and TPU. And frankly, not the only, because people who aren't into deep learning can use it for all sorts of other purposes, but maybe the main purpose was very large-scale deep neural networks, and so GPUs and TPUs clearly are the hardware of choice. It has a high-level, very NumPy-like API, which makes it really easy to get started. But it also has a lower-level API, and I'll mention briefly at the end, things can be pushed even further. The lower you go, the harder the coding gets, but the more efficient your code can be. And one of the particularity of this library is that it requires extremely strict functional programming, and I will talk quite a lot about that. So there's already NumPy, there's Numba, there are lots of deep neural network libraries, TensorFlow, PyTorch, others. PyTorch and TensorFlow, of course, are big. So why JAX? And this is something that I've already mentioned in another webinar because I find it tremendously useful. It's a little summary that I've made of a blog post by Chris Rakokas, and I really recommend that you read the whole post. And the post talks a lot about Julia because this is where Chris works. But taking off the Julia side of things, if we look at the history of the trade-offs around automatic differentiation through the various frameworks that have evolved over time, TensorFlow came first with a very efficient system working on XLA, which is the accelerated linear algebra tool set by Google, and that has very good performance. But it is based on a static graph. So it is really inconvenient for the user because the user has to manually write a graph. So all of the intermediate representation of the forward pass so that the automatic differentiation can be performed. So yes, it's efficient, but it's extremely inflexible and inconvenient. So when PyTorch came out with a form of dynamic graph where through the forward pass, automatically, without all of this inconvenience, the tracked tensors could keep in memory the computations that are performed on them, allowing for an automatic differentiation that is incredibly easy and convenient. PyTorch exploded in popularity, and that started the decline of TensorFlow. That said, the way PyTorch tracks the computations happening on the tensors so that the backpropagation can be done is on a one-per-one basis. It's each individual tensor with its individual value is kept in memory. So you can't do a lot of caching, you can't do a lot of optimization. So the automatic differentiation is it's not general enough to allow for good optimization. So with the decline of TensorFlow, Google launched TensorFlow 2, the eager TensorFlow, with an attempt at a dynamic graph that would work with their very performant XLA. So trying to have the convenience of PyTorch, but with the performance of XLA, and it was a big disappointment. TensorFlow 2 is not a very successful attempt. The speeds just weren't there because the XLA that was so good through the creation of a dynamic graph, again, couldn't be general enough to be to allow for good optimization. So this is where we are left off, and this is why Google has moved on from the TensorFlow projects and started JAX. So JAX uses XLA because XLA is really good, but it has an attempt of some pseudo dynamic graph. And I say pseudo, if you read the post by Chris, you'll see exactly why I say pseudo. It's not fully dynamic. There is no such thing in Python. Julia is really trying hard to get that done. But in Python, it just doesn't exist because of limitations of the language. Actually, the Google team, according to Chris, did attempt a fully dynamic system, but the language, the Python language, is just too limiting to get there. You need something like Julia or some other language to accomplish it. But it doesn't really matter because JAX is mostly used for deep neural network. And in this context, you don't have a lot of complex control flow with some if-else and things where you would want a real dynamic system. And so you end up with something that is very convenient, that has the convenience of PyTorch, where the internal representation is created automatically without the user having to write all of that in themselves. And you have a pretty optimized automatic differentiation. Now, there is a disadvantage, is that you need pure functions. It's this strict functional programming I've talked about. So how do you get started with JAX? First of all, you might want to install it so that you can run it somewhere. And wherever you want to install it, use wheels. Frankly, that's the best advice that both the official site and I can give you, because JAX is designed to work on accelerators, and if you install it, probably you're going to be trying to use GPUs. There are dependencies with CUDA and CUDNN, or if you're on Mac, some other dependencies, and it's going to be challenging to make it work. So you can follow the instructions on the official website and install the wheel that corresponds to your OS, and that should work easily. Now, probably, if you're interested in JAX, you will want to run things at a very large scale. So probably using supercomputers will make sense. And so if you want to work with JAX on the Alliance clusters, really it's important to install from a wheel. It's always better when a wheel is available for any Python library to use that wheel, because it's optimized for the hardware. It ensures that there's no problem with missing dependencies or conflicting dependencies. But in this particular case, it's particularly critical because it could be just hell to have the whole CUDA system work otherwise. And so how do you install from wheels on the Alliance clusters? Well, you have to make sure to use this no index flag. Now, a little note. I'm going to pass real quick the link to answer the chat. Windows users, the only support for GPU is with Windows subsystem for Linux. So if you want to stay within Windows, it's CPU only. But again, it doesn't matter if you're on Windows, because probably you'll want to use a supercomputer anyway. And it's still fine to install the CPU version on your machine so that you can prototype the code, because one of the beauties of this framework is that the code, the exact same code, can run on any device. So there is this high-level NumPy API. And if you look at the code, so this is NumPy, like the library I suspect a lot of you are familiar with. And if we look at the JAX NumPy API, like you can see, it's just the same thing. It's imported as JNP. It's the JAX NumPy module. And so, of course, we have JNP instead of NP, but we get the same thing. So they really tried to make a high-level API that would be super easy to get into, since NumPy is so popular. However, JAX NumPy is not NumPy. There are extremely deep fundamental differences, and they are very important. Little difference, not important, the type is different. The default type for the NumPy object is the ND array. With JAX NumPy, it's an array. But a little more important sometimes, be careful, pay attention to the default data type. The default data type for NumPy is the float64. For JAX NumPy, as with TensorFlow and PyTorch and any deep learning library or library that is designed to run on accelerators, the default is float32. So not only this is a lot better for deep learning, because you want to run as many computations as possible very fast, and the downside of the loss of precision is negligible, but GPUs are particularly slow with float64, much faster with float32, and GPUs cannot even run float64. So accelerators really, it's float32 or even lower. So the default type is just aligned with any accelerator-oriented library. Another little difference is that NumPy arrays are mutable. So if you create an array with NP arrange that just creates 5 integers in an array of length of the element that you apply to NP arrange, you can, by indexing one element and reassigning a new value, transform your array in place, no problem. With JAX NumPy, you cannot do that. You have to use this at with the index and then the set function to change the value. Well, not a big deal, but immutable arrays are at the core of JAX NumPy. And that might seem less efficient because you are creating a new object, but in fact, the compiler, if you don't need the initial object anymore, is going to optimize all that and get rid of it. So it looks less efficient, but in fact, it's not. the compiler work under the hood. The input control to increase efficiency is stricter. Even though NumPy has as the default object an ND array, you can throw a list or a tuple to the NumPy functions and everything works. With the JAX NumPy functions, you're going to get error message, like just reduce inefficiencies, no inefficient data types, like structures, sorry, accepted. Something a little quirky and weird, and something good to be paying attention to, because you can have silent errors. In NumPy, if you try to index out of range, you will get a nice error message so that you're not getting some funny result. With JAX NumPy, because of the way the compiler works, that's actually very hard to implement. And so JAX will happily and silently return the closest boundary if you index out of range. So you can get some spurious result if you're not aware of this. Another little thing, but not super important, the way to create pseudo-random numbers, so something that you will need all the time when you want to create any kind of random array, is very different than what you're familiar with from NumPy, R, Julia, etc. Usually the pseudo-random number generators are just based on some non-deterministic state of the OS at the time of your run the command. So you set a seed to make sure your code is reproducible, but then there's some repeated states that get used, and that's what is used to automatically create your like run your pseudo-random number generation. So it's super easy, it's very convenient because it's all automated, but it's actually slow, it's problematic for parallel executions. The fact that it repeats a number of elements, even though there's a large number of them, can eventually create problems. So JAX relies on a much nicer system. It's just a little bit more work for the user. So you explicitly set a random state that's called a key. So from the random module that comes with JAX, you run random.prng key with some whatever number that you put in there. You can think of that as the equivalent of the seed in the classic system. And that will create some array that's your initial key. Now, that key you can only use once. Every single key can only be used once. Think of it as it has like a budget of randomness, and once you've used it once, you absolutely shouldn't use it again, otherwise you can get some spurious correlations. But you also want, if you want your code to be reproducible, to have all of your keys connected to each other. So the cool thing is that those keys can be split, like they can be forked into any number of keys, 2 or more, with the random split function. So if we pass our initial key to the random split function, we can get 2 keys or many more keys. You can pass an additional argument to random split if you want more than 2 keys. That's totally fine. So now we have 2 keys in this case. Initial key we've used up here, like this random split is some kind of random function. So we've used up the randomness budget of the initial key. So we throw that one out. We then now have those 2 keys, and we can keep one that we can split in the future if we need, and use the other one to create some random array, for instance. Now, I've used a new key 1, new key 2, initial key, so that you can follow what object is what in this example. But a better way to go about this is to call the first one key, and then split it into key and subkey, so that the key that we have here, that's a new object that comes from the split, but we rewrite the old key by this new key, and that ensures that key, the name key is now associated with a new key, and it ensures that we don't accidentally reuse key. And then we have a subkey that we can use to create a random array in this fashion. So not a big deal, but just a little thing that can surprise you at first. But it's a much better system and solves a lot of issues down the line, particularly with parallel runs. Another little quirk is about benchmarking. One of the efficiencies of JAX is that it uses asynchronous dispatch. So when you launch any computation, instead of waiting for the computation to complete before you can do something else, the computation is automatically dispatched to an accelerator, assuming, of course, you're running on GPU or TPU, and you get a future returned instantly, very rapidly. And that future can be used in other computation as long as you don't need to print the result or return some calculations. Of course, if you want to print the results, then Python will have to wait for the computation to be performed. But as long as that's not the case, you can run your code without having to wait for the accelerator to be done with the computation, just using this feature. So that's great, but when you benchmark things, you don't want to benchmark the dispatch, you want to benchmark the actual computation. And so there is a method, block until ready, that you want to remember to use each time you do any kind of benchmarking. Otherwise, you're just benchmarking some dispatch, which is irrelevant. Okay, so little quirks, little differences with NumPy. Yes, NumPy. Now, let's get into the actual heavy-duty differences and like the JAX map, like the way this framework works. This is like the important part of this talk, and that's the one thing I hope you will live with, because this is really the most important thing to understand so that you can get started with JAX. This is a little schematics of the way JAX works under the hood. You need to start with some pure Python functions, and I will explain in the next slides what I mean by pure Python functions. But that's the Python code that you write. And the first time that you write this Python code, you have some tracers that are wrapped around the code and create some intermediate representation. So remember that with TensorFlow, you had the user had to create some graph, had to write those the intermediate representation, and so that was the tedium. This is done automatically through the tracing process, so that's great. And what you have, that intermediate representation is made of some JAX expressions that are called JAX PR. So those JAX PR are really great because they can be used through transformation. And the last transformation will be just-in-time compilation that will transform the JAX PR into some high-level optimized program, or HLO, which is the best program that you can then feed to the XLA that will compile it for the device that is available, CPU, GPU, or TP. Now, this process of tracing is very important to understand. What happens during tracing and the just-in-time compilation is that a program gets created and cached so that it can be reused much more efficiently instead of running the slow Python code. But what gets cached is a program that keeps the shape and the type of the array that has been used. So that means that you can change the value of like you can rerun the code with new arrays with different values, as long as their data type and their shape remains the same. You don't have to recompile everything and rerun the slow Python code. You run this really fast compiled and cached program. Very similar to what Julia does using static arrays. And recompilation is only forced if you changed the data type or the shape of the object. But this generalization, which allows optimization, comes at the cost that you can only use pure Python functions. Pure Python functions means functions that have no side effects and functions that do not use any variable that is not contained in the input. Pure strict functional programming is you have some inputs, some function, some output. The outputs only depend from the inputs. So it doesn't depend on the environment. And it doesn't transform the environment, so it doesn't print to the standard output. It doesn't transform anything anywhere. You just have input, function, output. So as long as you do this, everything works great. But if you don't, you'll see that your code will not do what you expect it to do. So I'm talking about transformations. What kind of transformations are we talking about? So one of them is automatic differentiation, so the calculation of gradients. Another one is the automatic vectorization, so that you can run in parallel entire batches of arrays, which is great for deep neural network. Another one is parallelization across multiple devices, multiple GPUs, for instance. And there are others. And all of these can be combined with JIT. So that's why I defined at the beginning JAX as being a way to create compositions of transformations of some array computations. So let's talk about JIT compilation, because this is a key part of the whole optimization of JAX. And if you don't use JIT compilation as much as possible, well, you might as well just use NumPy. You're not making use of JAX the way you should. So the syntax is very simple. You import the JIT module from JAX. So here is a quick demo of the way to create random arrays using the pseudo-random number generator we've talked about. So you create your key, you split it. Here we're splitting it in 3. So key is something that we keep because we may need it later on, but we now have 2 subkeys that are linked to our key. So reproducibility is thanks to this link here. So we can create 2 random normal arrays. And then we can have a function that uses those 2 arrays. And so that's our sum squared error function. Okay. So we could use our function simply by giving it some arguments, the 2 variables that we've just defined. But this would be just like using NumPy. What we want to do to take advantage of the efficiencies of JAX is to do some JIT compilation of the code. So the syntax works in several different possible ways. You can either create a new function that we can call sum squared error JIT, and you create it by passing our function into the JIT function. And then we pass the argument to this new function to get our value. And this will run a lot faster. You can also nest things directly. And in that case, the arguments get passed in a syntax that's a little bit unusual. Or there is a @JIT decorator that you can put before at the top of your function definition, and then some squared error in this case is just JIT compiled directly during its definition. Okay, so that's very easy. Now, there are situations where things will not work well, and that's why Chris Rakokos in this blog post says rightly that it's not a fully dynamic graph, and neither was PyTorch. There is some dynamism in that the user doesn't have to write the intermediate representation by themselves as with the first version of TensorFlow, but it's not fully dynamic. Why? Well, in this case, in the case of PyTorch, because the tracing, if we want, like the memorization of the operations done on the tensor are recorded on one individual tensor. So really not, like extremely narrow, specific, not good for optimization. Here it's much more general, it's much better, but we get into situations where we hit some problems. For instance, if we have a control flow situation. If we try to JIT compile this function, this conditional function, it will not work because the result depends on the value of x. And remember that the JAX PR doesn't contain the value. It contains the shape, the data type of the arrays, and the operations performed on them. But here, we do need the value to be able to compile this code. So that's a problem. So how do we go about it? Well, one easy option is simply to exclude the problem argument from tracing. And we can do that by passing static argnums to the JIT function here to exclude. So here it's the first argument, because we have only one argument, but you could exclude any number of arguments based on their position here from the JIT compilation. So of course, we're not optimizing everything here because we're excluding some stuff from the JIT compilation, but we're still at least just JIT compiling the function, and that's a lot better than not JIT compiling at all. We can exclude also from the argument name. So instead of static argnums, as we used here with the index, we can use static argnames with the name of the argument that we want to exclude from the JIT compilation. And here, that works. There are more sophisticated ways if you want to avoid to recompile for every single different value that you pass to your function. And that uses the lower end API, so LAX. So you import the LAX library. And then there's a LAX cond function, and you can compile the branches by defining the predicate, false or true, and the conditions, and then have your values. So this is really equivalent of what I had, but I have to define the path myself. So for this operand 2, I want the conditional here to be false to match what I had over here, and for -2 I want true. And there are a number of other control flow primitives. There's while loop, for I loop, scan, and some pseudodynamic control flow functions that allow you to go around this thing. And Chris mentions those in his blog post. It's not fully dynamic, but it allows you to jumping some little hoops, have things fairly flexible, and because in deep neural networks, if-else control flows are actually extremely rare, this is not a big deal. Similarly, you can have problematic operations that will not JIT compile. In that case, one easy way to go about that is to just use good old NumPy instead of JAX NumPy. Like here, for instance, JNP array will have as an argument X shape, and X shape depend on X. So we cannot know, without knowing the value of X, what shape will be used for this argument. And again, we need to have the data type and the shape for the JAX PR. So here we cannot create a JAX PR because we cannot know the shape of this array over here. So we can simply use NumPy for that situation. And that way, we can still use the JIT compilation, which is better than not using JIT compilation. So I'm still JIT compiling the function, but instead of having this JAX NumPy code in the function, I'm using npprod over here, because npprod can work, like it won't get JIT compiled because it's a NumPy function. So the fact that the shape of x.shape is unknown at compilation isn't a problem anymore. Those are little quirks of the JIT compilation. But when you JIT compile your code, as you should, you will get into issues if the functions that you write are not functionally pure. And I've said that a bunch of times, so let's cover some examples. By the way, if you want to visualize the JAX expressions, the JAX PR, you can do that thanks to the JAX make JAX PR function. So if you create a function f and then run it as an argument of JAX make JAX PR and pass to that the arguments of your function, you get some insight into the JAX PR. And if you print functions with side effects such as printing, etc., you will see that these do not appear in the JAX PR. They are not recorded as part of the JAX PR. So how to read this JAX PR? Well, so A, B, C, etc., those are the objects in the order in which they appear in this world. So A, for instance, is the first argument, so X. B is the second argument, so Y. F32 is the data type, they're float 32 by default. The digits between square brackets are their length. X and Y are arrays with a single dimension and the length of 3. So that's why we have a single digit here, and it's 3. And so so those are the A, B are our arguments. Then let is the computations that are performed on our arguments. So as I mentioned earlier, the JAX PR records the data type. It is indeed recorded in those F32. The shape, 3 here, 3 here, that's the shape. But the values are not recorded. And it also records the operations being performed. So the first operation performed is to take the power of 2 on A. So this is what we have here. Then the second computation is to do a multiplication of the result by 2. And then finally, we get E by adding D and B being Y. So this really shows you what is recorded in this JAX PR, the shape, the data type, and the computations performed. So it's a little bit like the idea of the PyTorch tensor tracking, but much more general, so it can be optimized much more. So what happens if you have some outputs that are not only based on inputs? So if you have a function that is not pure, for instance, a function f that returns a being some kind of variable from the global environment plus x. So x is fine, it's our input, but a is not one of our input. So not a pure function. Okay, so let's define a in the global environment. So GNP1s, you'll recognize the function similar to NP1s. We can print it. So we have an array of 1 dimension, length 3, with float 32 as a data type. Okay. Now we'll define our function. If we print the result of the JIT compilation of f, passing as the value for x another GNP1s, we get 222. So we have a, which was 111, plus x, which is 111, we get 222. So all seems good. Nothing seems at odd here. But that's because this is the first run, and during the first run, the actual Python code is run during the tracing process while the JAX PR are created. Now, if we change the value of a in the global environment, so if instead of having 111, we have 000, and we rerun our JITF GNP1s, instead of getting 111 as we should, we still get 222. Why? Because what happens in the global environment is not recorded by the JAX PR. And because we haven't modified the shape and the data type of what has been recorded in the JAX PR, JAX will use the cached compiled program that it has created to make the code very efficient. And that's great, that's what we want. But we get the wrong result because we're using a function that is not functionally pure. Now, if we change the shape of a, and that would we would have the same behavior if we change the type instead. Now we have to, JAX has to rerun the compilation and caching because the JAX PR becomes outdated here. And so here we get a result that seems correct again. But then at the next run, we'll have the same problem. So your outputs need to only be based on inputs. The other thing that I've mentioned are side effects. So printing to standard output, reading, modifying something that's not the output, all those side effects, they won't be recorded by the cached compiled program. So the first time you run the code during tracing, again, the Python code gets run, so the side effects will be run. So for instance, here we have a new function that depends on A and B, and the first thing it does is to print something and then returns the sum of A and B. If we print the JIT compiled form of f and pass as the values for the arguments A and B, JNP arrange 3 and JNP arrange 3, we do have the print calculating sum that gets run. So we have that output, and then we have the sum. So 0, 1, 2 plus 0, 1, 2, 0, 2, 4. Okay. So again, it looks like it's fine, but that's only because that's the tracing process. If we rerun the function, now that it's been cached and compiled, we're not getting the side effects. So you do not want your code to rely on side effects when you use JAX. Okay, so those are like the big differences with NumPy, the big things that you have to be careful of. But once you're familiar with that, then things get really cool because there's so much you can do with JAX. So I've mentioned one transformation already, the just-in-time compilation that allows you to optimize your code and have it run a lot faster. But there are other transformations. And one of the big ones is this automatic differentiation. And that's what makes JAX so great for deep learning. So here is a very, very basic example, super simple, from the JAX documentation. If we consider a function f, that's like x to the power of 3 plus 2x to the power of 2 minus 3x plus 8. Okay. We can super easily create a new function that we can call df/dx that will compute the gradient of f with respect to the first argument, which in this case is x. That's the only argument here. The way to do this super simply is to import the grad module, and then df/dx is simply a function that we create by passing the function f as the argument of the function grad. And then if we want to get the derivatives, we can simply use our new function df/dx. So it is insanely simple, and it's also very close to the math. It's very intuitive, much less intuitive than the way, for instance, PyTorch works. PyTorch, because of the way it records the computations performed on a tensor during the forward pass as some metadata of a tensor, then once you've calculated the loss, you do loss dot backward, which is kind of a little bit strange. Here, you don't do it from some tensor, from some value, you do it by transforming a function. It's just what the math does, so I think it's more intuitive, but mostly it's also very flexible. Transformations can always be composed, so you can JIT grad or grad JIT, note the syntax, very similar to the one we saw with JIT earlier. All those transformations can be composed together at will. Now, there are some more advanced automatic differentiation modes, such as reverse mode, VGP, and forward mode, GVP. And you can create super easily higher order differentiation. If you have a single variable, then it's really just a question of nesting the grad function calls inside each other. So to have the second order derivative that we could call d2f/dx, then we simply have to pass our df/dx, which was our first order derivative of f, itself into the grad function. And then to get d3f/dx, like the third order derivative, we would just pass that into the grad function. So you can nest the grad calls to get derivatives of derivatives of derivatives super easily. If you have several variables, it's a little bit more complicated, but you can do it with the JAX FWD for the forward mode or JAX rev for the reverse mode. And which one you want to use depends on the code. There are situations where one will be more efficient than the other, and vice versa. But so the automatic differentiation in JAX is really super flexible and really easy to play with, as long as you don't have these if-else situations that Chris talks about, but with deep learning, you just don't get them, so great. I don't have time to talk about them here, but there is one data structure that comes with JAX that's called a pie tree that is super useful for a deep neural network. A pie tree is some kind of nested container structure. You have pie trees, which are anything that are like a list, a dictionary, or a tuple, and then pie tree leaves, which is anything else. And so you can have all these pie trees with pie tree leaves, and that's super useful with deep learning because you can have, for instance, some metadata and all of your data and all of your batches in some complex ways, and all of that can be packaged super easily. And there are some util functions that allow you to flatten all that, to play with that, to extract elements or others, get the number of pie trees, the number of leaves, etc. And so it makes it really easy to play with deep learning when you have like all these layers of batches and data types and the weights, and yeah. So very, very useful container structure. Then other transformations that I don't have time in this very short introduction to talk about, but that you will use all the time in the context of deep learning are vectorization with JAX BMAP and parallelization across multiple devices with JAX PMAP. And when you will want to run batches and batches of data, this automatically transform the code that you had into some parallel runs without having to have to think about how you can vectorize or parallelize your code. You just transform it with VMAP or PMAP, and boom, that's it. Super conveniently, your code runs across batches and batches. And then to finish, for people who really want to push JAX to its limit of its current state of optimization, you, instead of using this high-level JAX NumPy that is super convenient because it looks so familiar, it's so similar to NumPy, you can use JAX LAX. So you have at the top the easy high-level API, JAX NumPy, but then things under the hood get turned into JAX LAX. JAX LAX is more powerful, it's more strict. For instance, it won't let you do some type, I forgot the word, but like if you say a float and an integer, it won't allow you to have this work, forgot the word, when you turn a type into another one to make something work. You can't do that because that's inefficient. So stricter, lower level, harder to write, but more efficient. And then JAX LAX itself is a wrapper around the XLA operations, because remember, the XLA is the accelerated linear algebra compiler that optimizes operations for the devices that you have. So there are those layers, and you can write at various levels of language if you want to optimize things further and further. But of course, it makes it harder to write the code. And then even though XLA, so remember at the beginning, at the bottom, we had this HLO, this high-level optimized program that was sent to the XLA here, and the XLA was optimizing the code for the CPU, the GPU, or the TPU. And the XLA is great, but OpenAI launched Triton, which is a very efficient way to write GPU kernels based on arrays. And so JAX launched Palace to make use of Triton without having to write Triton directly, because you still want to make use of all the JAX machinery and the fact that you're familiar with the JAX code. You can, thanks to Palace, instead of using the XLA, turn your HLO for Triton for the GPU. And the equivalent of Triton, but for the TPU, is a program called Mosaic. And so with Palace, you can also send your code to Mosaic for the TPU. And so this allows you, if there are situations where the XLA isn't optimal, it allows you to bypass the XLA and customize things directly in this fashion. So this is it, but I saw that there were some questions in the chat, so I'll try to answer them, and then I will try to answer any more questions. So let me, oh, and in case some people have joined us a little bit on the late, let me pass in the chat once more the link for this webinar. And again, I think JAX is excellent and powerful, so there will be more webinars, and we're currently in the middle of a 3-week course on JAX, a 3-session course on JAX that will be followed by the 3-session course on Flax. Because one thing that I did not mention is that JAX didn't want to reinvent the wheel where the wheel was working great. So PyTorch and TensorFlow and Hugging Face already have beautiful data loaders. So there is no way to create a data loader in JAX because there are all those other tools. So to do some deep neural network in JAX, you can use a data loader from TensorFlow or from PyTorch, for instance. Similarly, they didn't want to reinvent all of the architecture on like all the utility functions that allow you to create deep neural networks easily. So all of the optimizers and all of the functions that allow you to create your architecture. So on top of JAX, there are some libraries that take care of all of that. And the one of the great libraries and the one that is officially suggested by the JAX team to use is called Flax. And following the JAX course, there will be a Flax course, and I will probably give some webinar on Flax at some point in the future, because Flax definitely takes all of this framework for efficient compilation and transformation that is at the core of JAX, and build on it all of the tools to create deep neural network. Of course, you could build deep neural network in plain JAX directly, but it would be unnecessarily tedious. There's no point to write your optimizer and write all of the functions to define your architecture when something like Flax has it all built.